Hi everybody, let's start week 4 lecture. So this week we'll be looking at visual data exploration. I'm going to be talking about just an overview of data exploration, and then we're going to talk about two different things. The first is summary statistics, and then second of which are essentially text representations of our data. And then we'll be looking at a whole lot of different visualization methods. First off, one-dimensional visualization methods, also visualizing one attribute at a time, and then two-dimensional ones, visualizing more, so two attributes at a time or even more. So first off, let's look at an overview of data exploration. So what is data visualization? Well, visualization is all about the display of information in either a tabular or a graphical format. So here's an example. This is an example by Mike Bostock, and it's used in a library called d3.js, and we'll be looking at this a little bit later. So this visualization is Uber rides in 2012 by neighborhood in San Francisco, and you can see that the different neighborhoods are listed around the circle. It's called a chord diagram. The different neighborhoods are labeled around the circle, and there's a chord, or there's a line linking the rides between the neighborhoods. And actually on d3.js it's a really interesting example because I've shown all of the chords, but as you move your mouse over it, it shows more or less of the chords and gives you a little bit more information about it. But regardless, it's a really useful way to explore the data, and it shows what's happening in the data much more clearly than if you were to just use a table. So successful visualization requires the data to be converted into some kind of visual format. And the data characteristics and the relationships between the data items or the data attributes are going to be much clearer and going to be easier to see. They'll be analysed faster, more efficiently and reported on than they were in the original table of data. And you can see that in this example from Uber. It's really clear where the majority of the trips are, so between South of Market and the financial district, and you can see where people are making their trips. So what are the motivations for visualization? Well, humans are very good at recognizing patterns visually, and the motivation for doing visualization is to play to the strengths of people, to allow people to quickly absorb a large amount of information and to find patterns in it. Here's another example. This is a table showing a whole lot of people, friends, and where they want to have their birthday wishes made. So you can see person number A or friend A wants their birthday wishes on Facebook, and person number B wants it by email. And you can see that there's a whole lot of different kinds of channels for birthday wishes: Facebook, email, Skype, phone, SMS and Twitter, and then what the people most prefer. But it's really hard to see anything from this table. It's not a clear way to represent the data. A much better way to visualize it is with something like a pie chart here. And you can see quite clearly that most of the people would want their wishes by Facebook, and then after that it's by phone, and then after that SMS or Skype. And the least people want to do it by Twitter or by email. So you can see that it makes a big difference how you represent the data. Now, we're going to be looking at one data set over several weeks of this semester. And so I want to go through that data set in a little bit of detail. It's quite a famous data set, and it's called the iris data set. In fact, it's probably the most famous data set in machine learning. And the guy on the right-hand side, the very distinguished looking gentleman, is a guy called Ronald Fisher. He was a biologist, and in 1936 he generated this data set. It's called the iris data set. It records measurements and species of 150 different species, of 3 species of iris and 150 instances in total. So 50 of each of the three types. There's iris setosa, there's iris versicolor, and there's iris virginica. And for each one of these flowers, of the 150 flowers, there are 4 attributes. There's the length of the sepal and the width of the sepal in centimeters, and then there's the length of the petal and the width of the petal in centimeters. And the idea is that using these 4 measurements, can you predict which type or which class of iris there are? This is a picture of an iris, just to point out what the sepal and the petal are. So you can see these sticking up things in the middle. They're the petals on the iris, and the sepals are the big floppy things that are hanging out the sides. This is a picture of the 3 different types of iris, and you can see that to the uninitiated iris naive viewer, they all look the same, but actually they're quite different. So the one on the left is iris setosa, iris versicolor is the one on the top right, and on the bottom right is iris virginica. And from just looking at that, it's a bit hard to tell the difference between them. This is a subset of what the data looks like. This is the first 19 rows, and they're all setosas, and you can see that there's a sepal length and width, and a petal length and width, and then the species of flower. So we're going to be coming back to that data set throughout the class in the coming weeks. For example, later when we start to talk about classification, we're going to use iris to classify. And it's a really nice data set because it's really, really easy to classify, it's really easy to do clustering, and it's really, and because it's only 4 dimensions, you can pretty much understand and visualize it in your head, as you'll see later in this talk. So first off, let's look at summary statistics. So summary statistics are quantities that capture various characteristics of a potentially large set of values using just 1 or 2 numbers. And you already know a whole lot of summary statistics, for example, the mean, the standard deviation, or the median. So let's look at a couple of different kinds of summary statistics in order. The first one we're going to look at are frequencies and the mode. So when we have unordered categorical attributes, the only thing we can compute is really the frequency of particular values. And you can see that the first formula underneath that is the frequency of value v sub I is the number of objects in the data set that has that value divided by the number of objects. And the mode is the attribute value that has the highest frequency in the data set. So let's have a look at an example. So here's a table of grades. So we have high distinction, distinction, credit, pass, and fail. And this is the grade attribute for 100 students. The second column is the number of students with that grade. And if you were to add them up, it should add up to 100. So you can see, for example, that 10 students got a high distinction and 40 students got a pass. So the frequencies are in the last column, and we got the frequency just by dividing the number of values for that attribute divided by 100, because that's the number of data points. And the mode is the value that has the highest frequency. The one that has the highest frequency is 0.4, and the grade that has that is pass. So that means that the mode is pass. So that's a little bit boring. Let's move on to ordinal attributes, because now we can do something a bit cleverer. So with ordinal attributes, we can compute percentiles. The idea here is that for p, the percentile value between 0 and 100, the pth percentile, x sub p, is the value of x such that p% of the values are lower than that xp value. So for example, the 50th percentile is the value of x where 50% of the values are less than that value. And by convention, x0 is the smallest value of x because there's no values underneath that, and 100 is the largest value of x because everything's below that. The next one we're going to look at are the mean and the median. And these are the measures of the location of a set of values. And they're only used for continuous attributes. You can think of them as being middle of the set of values. So the mean is the average and the median is the middle. And they don't necessarily have to be the same value. So with a normal distribution they are, but lots of distributions they're not. If the distribution is skewed, or if the distribution has outliers, then that moves the mean and it moves it away from the middle. So in the cases where you do have outliers, often you use the median instead of the mean. And they're defined as follows. So the mean of x is x bar, and it's just the sum of all the values divided by the number of values. So you would be very aware of that one. The median depends on the values in the data set. So what we do is that x sub and then the brackets r, or r plus 1, means that we're going to order all of the x's in increasing order. So if there's an odd number of values, then the median is the one in the middle. And if there's an even number of values, then the median is the average of the two that are right at the middle. So that's the location of the values, the middle of the values. The other thing that we can do with continuous attributes is to measure the spread of the values, how spread out the data is. And a big value of this means that the data is quite spread out. So here we have range and variance. So range is just the maximum value minus the minimum value. And variance is, or S squared, is each value minus the average, so that's centering the data, taking the square of that and dividing by the number of values. So variance, because it's dealing with this, it's using the average or the mean. It's also affected by outliers in the same way that the mean was. So there's extensions to the mean and the variance when we have multivariate data. So the mean becomes a vector, and you can see that in that first one, in the first formula there. And the variance changes to be captured with something called a covariance matrix, and that gives the covariance between each variable. So we can see S sub ij is the covariance between I and j, and it's just it's quite similar to what we did with the variance here. Instead of squaring it, we're doing it with two different sequences. However, covariance isn't really a very helpful way to measure the degree of relationship between the variables, and the reason for that is because it can vary quite wildly, quite a lot, depending on the range of the sequence. So we're usually better to use the correlation matrix R instead of the covariance matrix S. And what we're doing with the correlation matrix, you can see below, we're just taking the covariance of between I and j and dividing it by the square root of the variance. And it just essentially normalizes the covariance. So there's a whole lot of other summary statistics that we might want to use as well. Perhaps the two that might be useful for you are the skewness and the kurtosis, and they measure the amount that the distribution is either skewed to one side or distributed around the mean. Usually what we do though is to draw a histogram of the attribute values, and that will show you the frequency for each of the values. And with a continuous attribute, it's almost like we're essentially getting a frequency for each binned section of the attribute. So it's really easy to calculate all of these statistics, the min, the max, the mean, the standard deviation, the variance, skewness and kurtosis, and the median in KNIME. All we need to do is use this statistics node, and you can see that on the right hand side. When you do that, you get a big table, and I've shown the values just for the petal length attribute. And you can see on the right hand side that it's a bimodal distribution, or at least at the level that we're looking at it there. So that's our summary statistics. Let's look now at visualizing distributions. So, as I said before, we can either look at distributions one attribute at a time, or we can look at them at several attributes at a time. So first off, let's look at single attributes at a time. So there's several choices here, and we're going to go through each of these in one by one. The first is the histogram, and that can easily show one attribute, or you can have three-dimensional histograms as well, although we're not going to look at them. And a histogram normally shows one attribute. A three-dimensional histogram will show two attributes. We can use box plots. That allows us to, we can also use that to show more than one attribute at a time on the same diagram. And pie charts, which you're probably quite well aware of. So let's look at histograms. So we can draw histograms quite easily in KNIME using, there's two different nodes. We can either use the histogram node, or we can use the interactive histogram node. And you can see a histogram here for one of the attributes of the iris dataset, and you can see it's binned each of the values. So the first bin, which may not be visible, but it goes from 4 to 4.392, and then the next one goes from over 4.392 to 4.784, and you can see that we've binned the attribute, and then the histogram, or each block, shows the frequency of the number of data points that have a value inside that range. This next slide is showing a box plot. And box plots are sort of cool. This is sepal width, and what it's showing is it's showing where the data is distributed. So we've got several things on here. So starting from the bottom, it's talking about the sepal width attribute. Forget that little dot that says 2.0, that's an outlier. Then we've got this big block in the middle, and that's showing where the 25th percentile value to the 75th percentile value for sepal width lie. And then the outer ones, the one at 2.2 shows where the 10th percentile is, and the one at 4.0 shows where the 90th percentile is. So it's showing where the data is sitting inside the range. At the very top, there's three values, 4.1, 4.2, and 4.4. They're outliers, so they're outside the 90th percentile. They're above the 90th percentile. And the line in the middle at 3.0 shows you where the 50th percentile is. So essentially where the median of the data is. And this allows you to see where where most of the data, the bulk of the data, is situated. And you can draw this using the box plot node on that we're showing on the right hand side. Now you can show lots of box plots next to each other, and that allows you to compare the distributions. So this is an example here. Here we've got a box plot of sepal length, sepal width, petal length, and petal width. So the four different attributes in the iris dataset, and you can see that their distributions vary quite a lot. Sepal length in general is much higher than sepal width. Petal length has a very wide distribution from the 10 to the 90th, and even between the 25th and the 75th percentile. And you can see, because the 4.35 is way up near the 5.1, it's not in the middle of that rectangle. That shows that the data is skewed towards the lower side. And then petal width is it's also skewed, but it's a lower range of values. So you can see quite clearly how the different distributions of these variables are. Now there's another type of box plot called a conditional box plot, and this allows us to condition the values over say a categorical attribute. So this one is looking at sepal length. Sorry, I had to go back and see. This looks at the sepal length values. So you can see it starts for each of the different classes of iris. So sepal length for setosa, the values range from 4.3 to 5.8. For versicolor, the sepal length ranges from 4.9 to 7, and for virginica, mostly from 5.6 to 7.9. So you can see there is a difference between the three types of iris based on this sepal length. And often this will show quite clear patterns that you can then interpret and will give you an understanding of which attributes might be useful for doing a classification between the different classes. Finally, for the one-dimensional visualizations, we've got pie chart. This is just a really simple pie chart of the three different classes of iris, and you can see that we have setosa virginica, versicolor, and there's a third of, we've got 33%, that's the percentage of the data of that class, and you can see it, they're equal, which we knew anyway, there's 50 of each. And you can get pie charts in KNIME using Pie Chart Interactive. So let's look now at visualizing distributions, so looking at more than one attribute at the same time. We're going to go through several possibilities. The first one, it's not strictly it's not strictly showing more than one attribute at a time, but it's a way of sort of doing that. What we're going to do is we're going to color by class. Next, we're going to look at scatter plots, so that we can look at two attributes at a time. We're going to look at scatter plot matrices, and they plot multiple scatter plots. So we can plot by twos all of the attributes in our data set. We'll look at correlation plots, and they plot the Pearson correlation between different attributes, and then parallel coordinates finally, where we can plot all of the attributes at the same time, and they're quite cool. So first off, coloring an attribute. So we can do this using the color manager. So what we do is we have our data node leading into the color manager node, and at the color manager node we can associate a color with a particular attribute. And usually what you do, and what we've done in this case, is to associate a color with the value of the class attribute, so for the different flowers. And then if you take the output of the color manager and put it into a histogram, you get this kind of thing that you can see on the left. So this is a histogram of one of the continuous variables, and you can see that one class in red is all the low values, and then mostly the blue class have higher values and the green class is the middle. So you could use this attribute to distinguish between the reds and the greens and blues. This is a scatter plot. Here we're plotting sepal length along the x-axis with sepal width along the y-axis, and each of the little squares is one of our data points. And we've again used the same trick of using the color manager to color the attributes the right colors. And you can see that quite clearly there's a cloud of reds. The reds are actually setosas. So it's a cloud of setosas that have quite different values of sepal length and width. So if we want to look at several scatter plots together, then we use something called a scatter plot matrix. And in KNIME, you use a scatter matrix. So this is plotting, so it's 4 by 4. So it's just taking each attribute in turn. So for example, on the top left, we're plotting sepal length with sepal length. That's why it's a line. And you can see, for example, petal on the bottom, the third one, bottom row, third from the left, we're plotting petal length with petal width. And you can see that distinguishes the classes actually pretty well. So again, you can use this type of visualization to understand what are good attributes for distinguishing or characterizing or classifying the data, and petal length is quite useful. The next one is the correlation plot. So this is showing the Pearson's correlation, a linear correlation between each attribute. We saw the correlation in the summary statistics before, and this is just a plot of that kind of thing. So we use the linear correlation node in KNIME, and it gives us it gives them in values, but we can also see diagram. So the diagram is showing here sepal length by the different attributes by with each other. So you can see, and then the colour is the correlation. So if it's a really vibrant red, that means the correlation is -1. So that's saying that there's a negative relationship between the attributes. And if it's blue, the bluer it is, then the more positive the correlation. So for example, you can see that. So of course we've got along the diagonal, we've got a correlation of +1 because sepal length, for example, is perfectly correlated with sepal length, and sepal width is perfectly correlated with sepal width. So this is showing that petal length and petal width are quite strongly positively correlated, and sepal width is negatively correlated with the petal values. We can use a correlation plot often to work out which attributes to get rid of if we need to do feature selection, if we want to choose less attributes. So if petal length and petal width are very strongly correlated, then maybe we only need one of those to make the classification. Okay, the final visualization that I want to show you through KNIME is parallel coordinates, and these are really cool. Use the parallel coordinates node from KNIME, and what it's showing, so it's showing quite a cool thing. So the lines are data points. So every line is one data point in your set, and along the bottom we've got sepal width. So the first that first column is the values of sepal width, and the line, if the line joins it, that says that that data point had that value of sepal width. So for example, at the very top of the first line, you've got a line coming down at 4.4. So that's showing a data point that had the value 4.4. And then the second column is a sepal length, then petal width, petal length, and finally the species. So you can see how the data clusters. So for example, what we saw before was that petal length, and to a limited, lesser extent, well, petal width and length can discriminate quite clearly between setosa and the virginica and versicolor, and you can see that really clearly in this diagram. You can see that sepal length is not very good at distinguishing anything, and sepal width to some extent separates between the setosa and the others. You can see that petal length is also reasonably good at distinguishing between the versicolor and the virginica. So this is it's a really good way to visualize the data. In KNIME, it's quite interactive, so you can change from having these curly lines to straight lines, and you can change the order of the attributes in the diagram. So there's a whole lot of other nodes in KNIME that you can use to visually explore the data. If you go into the node repository, like the diagram on the right hand side, and if you look at in data views or in statistics, then you'll see the nodes that are useful, and you can see there's a whole lot more that we didn't go through in this talk. Now I want to talk about another couple of visualization tools. The first is a JavaScript library called d3.js. So it's called Data-Driven Documents, and the URL for it is just there. It's a JavaScript library for visualizing data, and it's really, there's some really cool examples in there, and it produces some really beautiful visualizations. So this is just, the pictures on the right hand side is just a couple of examples from their example list, and you can see it does box plots, but it does a whole lot of other interesting kinds of visualizations. You need to do a little bit of programming in JavaScript to make them work. The other tool that I want to show you is called Gephi, and Gephi is a tool for visualizing networks. So we can often describe our data as in some kind of graph or network form, and we can use a tool called Gephi to be able to visualize that data and to show how it links together. So if you go to gephi.org, you can get access to that tool. It's so both D3 and Gephi are open source free tools, and 9. Okay, on this last slide, I want to talk about just a couple of principles for designing good graphical displays. So a guy called D.A. Byrne devised these accent principles, and the principles for doing effective graphical display. Accent stands for the first letter of each of them. So the first is apprehension. Apprehension is all about the ability to be able to perceive relations between the different variables. So ideally, we want to be able to see those relationships clearly in the visualization. The next one's clarity. So clarity is all about how well we can distinguish all of the different elements. Is it really cluttered together, or is it quite clear and open? The next one is consistency. So consistency is all about how we compare different graphs. So can we is the way that we interpret this particular graph similar to the way that we interpret previous graphs? So it really feeds into this idea that people get used to seeing things in particular ways, and then they can use that to understand the other graphs. Next one is efficiency. So is it easy for people to interpret? Is it efficient for your brains to interpret the visualization? Next one is necessity. So what is the need for the graph? Do we need to see this data? And finally is truthfulness. This is the ability, it's how well the graph doesn't lie to you. So what's the ability to determine the true value of an element by its magnitude compared to the scale of the graph? So that's the week 4 lecture, and I'll see you in class.